Good morning, AP Chemistry. It is Tuesday morning, the week of Thanksgiving, and this is going to be the last section of Chapter 7, and this covers the periodic trends. Please make sure you know the trends, you know why the trends occur that way, and the exceptions to the rules, because of course, like all good chemistry concepts, lots of exceptions to the rules, so you have to know all three things. Also, for shortcut, I usually abbreviate, and in this order it's going to be atomic radius, AR, ionic radius, IR, ionization energy, IE, and electron affinity, EA. Notice that electronegativity is not on the list because we are going to hit that hard in Chapter 8, which is the bonding chapter. So electronegativity later. Alright, when you are determining and understanding trends, a couple of things to consider when you're doing this concept. And it is all concept. There's absolutely no computation here at all. It is all conceptual. Alright, thing number one, the proton-electron attractive forces. This is the force between the nucleus and electrons about the nucleus in the Schrödinger or quantum mechanic orbitals. The electron-electron repulsive forces. This is the repulsive force between like-charged electrons. Shielding. The effective nuclear charge felt by the valence electrons. Shielding of the valence electrons by core electrons. And core electrons shield valence electrons, but don't shield other core electrons. Size of the orbitals. Keep in mind that as n increases, n is the principal quantum number which depicts energy and size. Type. Is it spherical, which is more penetrating towards the nucleus than the dumbbell-shaped P or the clover-leafed Ds? And pairing of electrons in orbitals for especially the very first time. Parallel spins, the Hund's rule, parallel spins in degenerate orbitals is lower energy than opposite spins in a single orbital. Alright, atomic radius is first. The effective nuclear charge, or ZEF, is the positive charge felt by an electron. The larger the effective nuclear charge, the greater the proton-electron attractive force. In other words, the more protons, the greater the proton-electron attractive force. The chart below kind of lists the first four elements in period number 3. So this is a trend that is going across the periodic table. Notice that the number of core electrons is constant. What changes is the number of valence electrons from family number 1, 2, 3, and 4. Those are the family numbers. So total number of electrons is the Z, core electrons is the 10, the effective nuclear charge is technically the valence electrons. And what does the radius do that's been calculated? The radius is decreasing as you go across the table. So these are pictures. Notice as you go across the periodic table, what's the atomic radius doing? As you go across, your AR is decreasing. And as you go down, your AR is increasing. Atomic radius is half the distance between the nuclei of identical atoms. And the reason it's that way is because atoms don't have a defined edge. Radius is measured as half the distance between nuclei. So they measure the distance between two like nuclei and then cut it in half. The trend for atomic radius is that it decreases going across the table, increases going down. The atomic radius trend makes sense. As you go left to right or across the periodic table, you're increasing the number of protons, aka increasing the nuclear charge, Electrons are being added to the same principal energy level, going across, mind you. So as you're going across period number 4, you're still in period number 4, but you're adding protons and electrons to it. So the electron cloud gets drawn in closer to the nucleus and has a smaller radius. So left to right, the atomic radius will decrease because there's more proton-electron attractive force. It has the same energy level. There's very little shielding going on. And the nucleus will have a tighter hold on those electrons. From the top down, the atomic radius is going to increase. There are more energy levels because, of course, now you're talking about the 5th, the 6th, the 7th energy level, which is N. The electrons are further from the nucleus, so it's getting a larger atomic radius. All right, ionic radius, IR for short, and there's two types of comparisons. We will compare an ion to its neutral self, or we will compare a bunch of isoelectronic ions, and isoelectronic ions means same number of electrons. The ionic radius in comparison to a neutral atom is very simple and very similar to weight loss or gain. A cation, which is the loss of electrons, will always be smaller than its neutral self. Losing weight, smaller. Losing electrons, smaller. And an anion, which is gaining electrons, will be larger than its neutral self because it, of course, is gaining electrons, aka gaining weight. When the cation loses electrons, you've removed an electron from the atom. You have protons basically covering each electron. When you remove an electron from the atom, that proton is still there. That proton needs to cover, and I'm doing air quotes here, needs to cover an electron. So it shifts its attention to another electron. So of course, as you remove electrons from an atom, the proton-electron attractive force is going to increase because each removal of an electron causes a proton to shift its attention to the remaining electrons. So a cation is always getting smaller. An anion is going to get larger and larger and larger because you're putting in electrons and you've got electron-electron repulsive force going on. The neutral atom sodium versus the ion sodium, and the ion sodium is smaller than the neutral. For chlorine, just the atom, mind you, not the element, so the chlorine atom versus the chloride ion, the chlorine atom is smaller. Or the chloride ion is larger, whichever way you want to look at it, because they follow the trend. So this is compared to neutral self. These are isoelectronic ions. Every one of these ions has 18 electrons. And in order of smallest to largest, you would write them this way. So the larger the nuclear charge, in other words, the larger the charge on the ion, the tighter the pull on the electrons, the more massive the proton-electron attractive force. So the more positive ion is going to be the smallest. So the more positive to the more negative, you would list them in that order. So, and I threw phosphorus in just for fun. Ionization energy. And there's more than one ionization energy for every element on the periodic table. If you got the energy, you can remove electrons, but you better have that energy behind you to do so. Ionization energy is the minimum amount of energy required to remove a single electron from a gaseous atom in its ground state. And the examples given is first ionization energy, second ionization energy, third ionization energy of a single gaseous atom. And like I said, you can remove as many as you like as long as you got the energy behind you to do it, because each successive ionization energy of a single atom will increase, because the more electrons you remove, the tighter the remaining electrons are held, and the more energy it's going to take to remove those remaining electrons. The trend for ionization energy is opposite to the radius, because of course the smaller the radius, the more energy it's going to take to scoop that electron out. The trend for ionization energy increases across the table, decreases down. And once you start digging into those core electrons, the ionization energy jumps substantially. I mean, it's already increasing. Each valence electron that gets removed, the successive ionization energies get larger. But the minute you start going into those core, it's a huge jump. Ionization energy trend makes sense. From left to right, the smaller the distance between the proton and the electron, the tighter the electron is held, the harder it is to remove. So you're going to have a lot of energy to remove that electron that's really close to mama nucleus. Going down makes a lot of sense too. That last valence electron, especially like think about francium, it's in the 7th energy level. There are 86 other electrons in front of it. That baby valence electron in the 7th energy level is so far removed from mama nucleus she probably doesn't even know it exists. Not a lot of energy to remove that one. There's a huge jump in the second ionization energy for sodium, which there should be. Each successive ionization energy should increase, but the size of the increase is enormous for the third ionization energy for magnesium. Now give a little thought to what I just said about ionization energy. The question here says, why is there such an enormous jump for the third ionization energy for magnesium and not for sodium? Well, look at the periodic table. Sodium has 1 valence electron, magnesium has 2. The answer is sodium, that first electron removed, is a valence electron. So not only is the second ionization energy going to increase, it's going to increase substantially because now you're removing a core electron. So the minute you start digging into core electrons, the jump in ionization energy is enormous. For magnesium, the first 2 are valence electrons, so the second ionization energy increases, yes. But that third one increases substantially. So here's a little chart. Take a look. Notice that the ionization energies increase incrementally. That's about 1200 increase, about 1100 increase, approximately another 1200 increase. But look here. So here's ionization energy number 6. And here's ionization energy number 7. It's an enormous jump. It's like twofold. That's because this guy here is a core electron. That is the 7th electron removed. That is the core. Sulfur is in family number 6. These first 6 electrons are valence electrons. And the minute you dip into the core, it's almost twice as much as the previous one. So it's an enormous jump. Alright, a couple of minor exceptions to the ionization energy trend. The trend for ionization energy is it increases going across the table. And most of these exceptions are usually going across the periodic table. But there's a little bit of a dip going from magnesium to aluminum. Why? Well, magnesium is filled. That's the 3S. Gets filled. And Aluminum is going to be the first electron in the 3p, and that filled s orbital provides just a small amount of shielding for the p orbitals. So there's a little enlargement going on there. So you get just that little bit of a dip, and most of the time these little anomalies occur when you're first filling the P after filling the S or doubling up on electrons. There's a decrease in ionization energy going from phosphorus and sulfur, and this is actually the entire family number 5 to the entire family number 6. It's not limited just to phosphorus and sulfur. So you get a small decrease in ionization energy, in other words, a small increase in atomic radius, because remember, ionization energy is opposite to atomic radius. So you get this small anomaly going on between family number 5 and family number 6, where the atomic radius actually increases and the ionization energy actually decreases slightly. And the reason that's occurring is for family number 6, when you're doing the electron configuration, for family number 6, you're suddenly putting an electron in an already filled orbital. It's experiencing an electron-electron repulsion for the very first time, and it expands slightly. So the atomic radius increases just slightly in family number 6. And with the atomic radius increasing slightly, the ionization energy is actually decreasing because they're opposite. And then, of course, once you get to family number 7, it's used to the pairing up, so it kind of recalibrates itself. It kind of gets itself back into shape. So you've got pairing for the very first time going on in family number 6. You get repulsion occurring, so you get a larger atomic radius and a smaller ionization energy. And it occurs between the entire family number 5 and the entire family number 6. Once you get to 7, all is well, and it's happy again. All right, electron affinity, EA for short, not to be confused with electronegativity. The definition of electron affinity is the energy change associated with adding an electron to a gaseous atom. It's the amount of energy released when you put an electron in a gaseous atom. So the more negative means the more released, and that's a good thing. So that really highlight that last two statements. More negative is better. More negative means the more energy released, the less energy retained by the atom. Because again, it comes down to stability. The more energy released, the less retained. That's a good thing. If you're trying to shove an electron into a gaseous atom and you need a large energy source to hold it there, that's unstable and that thing will blow. So the more released, the better, because the more released, the less retained to hold that electron in that gaseous atom, and that's going to be good. The trend for electron affinity, the greater affinity, meaning the larger amount of energy released, means an atom wants an electron more. Affinity value is a more negative number. More energy is released, less retained when that electron is added. And if you think about it, which side of the periodic table is supposed to have gained electrons? Well, the right-hand side. That means the right-hand side of the periodic table has an affinity for the electron. So I would expect that the electron affinity is more negative on the right-hand side and more positive on the left-hand side, because I don't think sodium is supposed to gain an electron. I'm pretty sure sodium's supposed to lose it, not gain it. So I think that the electron affinity for sodium might be a little too positive, because it's not supposed to gain. It's supposed to lose. Okay, electron affinity trends from left to right. It becomes more negative. In other words, right-hand side of your periodic table, upper right actually, is going to be the more negative electron affinity. it releases more energy up in that right-hand corner. The atoms are smaller. They hold the electrons in nice and close and tight. Attaching an electron to that proximity of a nucleus will release more energy, retain less, and that's a nice, stable, low energy concept. If you're going from top to bottom, generally the electron affinity comes closer to zero, less negative. So less energy is being released, more is being retained. That's not a good thing. The atoms are larger down at the bottom. They hold the electrons less tight. They're loosely held electrons. You're attaching an electron that's really far from the nucleus, and it's going to release less energy, retain more, so it's not a good thing. And just so you know, to bring this thing home, magnesium has an electron affinity of a positive 78 kilojoules per mole. That means there's an external power source actually needed to hold the electron in the atom. So picture someone holding a wall up that's trying to topple over. You have an external energy source holding the electron in to the atom of a magnesium because it's not supposed to take on an electron. So there's an external source. All right, so here are the electron affinities for the halogens. Halogens are on the right-hand side of the periodic table. Halogens are supposed to gain electrons. So their amount of energy to be released when they're gaining these electrons in the gaseous state should be a large negative number. Electron affinity will get smaller as you go down the periodic table. So this follows the trend. Now, exception to the rule. Notice that the fluorine is a little odd. Shouldn't fluorine be the highest electron affinity? And it's not. And the scientists aren't even sure. They think that because of the size of the p orbitals for fluorine, and the closer those are to the nucleus, that the electron affinity is smaller. All right, so here's what I want you to write down. Alright, so in terms of trends, as you go across the table, left to right, atomic radius decreases. As you go across the table, left to right, ionization energy increases. They are always opposite to each other. Ionization energy, the amount of energy required to remove an electron from a gaseous atom. The stronger that electron's held, the more energy it'll take to remove it. Electron affinity going across the table generally will increase, which I would expect right-hand side should have a higher electron affinity than the left-hand side. Just described how magnesium actually has a positive electron affinity. Going down the table, atomic radius increases. You got 765 energy levels getting further from the nucleus, so I would expect the radius to increase. Ionization energy will decrease. The further away the electron is from mama nucleus, the easier it's going to be to snatch it. And then electron affinity is going to decrease, it gets smaller, and in terms of electron affinity, that usually means a less negative number. And that's the trends.